Okay, so we're going to talk about the lead acid battery. You don't need to be able to recall the details of this for AQA Chemistry A-level, but it's the kind of thing they could give you where they'll give you some information, you have to interpret it. So here's the lead acid battery. It consists of, as you can see here, we've got 2 lead electrodes in a solution of dilute sulphuric acid. As we'll see, the positive electrode, this one here, is actually, when the cell is charged, it's coated with a thin layer of lead 4 oxide. Okay, so let's have a look at the 2 half equations. So let's have a look at this one here. Right, which we're going to see what is going to happen when we run that cell down. Well, the most positive half equation is this one. So that's going to be the best at positive, best at pulling in electrons. So that one is going to pour in electrons. That's going to tend to go in the forward direction. And then we predict this is the more negative one, it's the best at giving away electrons, so that's going to tend to push out electrons and go backwards. So we write down the cell reaction there then. What's going to happen when we run that cell? We're going to get lead oxide and the 4 protons from the sulfuric acid and lead metal, and that's going to give us 2 Pb2 plus ions and water. That is what happens when the cell is discharged. Okay, so when you're using it to provide a current. So I just draw the arrows on that show the direction of the electrons on the diagram. They're going to come out of this negative electrode here. This is the negative one. As the lead turns into lead 2 plus ions, goes through the load of a battery, and it's going to come to reduce the lead 2 oxide on the surface of this electrode here into lead 2 ions. That is what happens when you discharge. So and if we look at E cell for that under standard conditions, we can see E cell, which is equal to E right minus E left. So we're going to get 1.46 minus 0.139. So we would expect to get a voltage in standard conditions of 1.60 volts. Now, we actually get a higher voltage than 1.60 because we are not, this is not under standard conditions. We see why it's not under standard conditions. It's all due to the fact that you've got sulphate ions, so you've got lead ions in solution here, and you've also got sulphate ions from the sulfuric acid. Well, lead sulphate is actually very insoluble, and so you're going to form a precipitate of lead to sulphate. Now let's see what would that do to the E cell value. Right, now so look at the lead 2 plus ions there. I'll do this in green, I think. The lead 2 plus ions there. Right, the E cell value is when they're at 1 mole per decimeter cubed lead ions. It's going to be nowhere near as high as that because it's going to be very low concentration because nearly all of it precipitates out. So Le Chatelier tells us if you have very low levels of that, it's going to push the equilibrium in the forward direction. In other words, it's going to be better at taking in electrons. So this will actually be more positive. It will be greater than 1.46 volts. And let's have a think about what would happen with the other electrode. Well, again, we've got lead ions there, and the standard value, minus 0.13 volts, is when you have 1 mole per decimeter cubed. It's going to be an awful lot less than that because it's precipitating out with the lead sulfate. So that is going to be more negative. So that means the E cell value, you've got, this one is more positive, this one is more negative, so that's going to be bigger, and it's almost 2 volts when the cell is run, and that's because you very low concentrations of lead ions. So that's good because it gives us higher gives us a higher voltage, but there's also other advantages to be had from that. And I'll just rub some of this out, and we'll have a little think about what examples. There's, by the way, here is the standard cell diagram for that. I'm not going to worry about that. Get rid of that. Sorry. Okay, now let's have a think about the lead ions. Now, normally, when you run a cell, you can see that you would expect, if we didn't have the lead sulphate there, the lead ion concentration, well, this is going forward, so that would get higher. I'm going to rub these out here now as well. When you run the cell down, imagine there's no sulphate ions, and also, because this one's going to go backwards, that's going to get higher as well. What effect would that have? If we're not precipitating out that lead, what effect would it have on E cell? Well, if this gets higher, it's going to push the equilibrium backwards, better at giving out negative electrodes. It's going to make it more negative. So that, if the positive electrode became more negative, E cell would drop. Also, what would happen here? Well, lead is becoming higher here, so Le Chatelier tells us that's going to push that one that way. Better at taking in electrons, that's going to become more positive, which would also mean that the E cell value would drop. So if you use the lead battery under conditions where you didn't have sulfate ions, and if you had lead, hydrochloric acid in there, lead chloride is soluble, then the E cell, because that would drop. And that's because the lead ion, the Pb2 plus concentration, would increase during discharge of that battery. By having sulfate ions there, you precipitate out all the lead ions here, as we've got here. That is advantageous because that, number one, it will stop E cell dropping during the discharge. And number two, we saw earlier on, I just said E cell to start off will be higher. Instead of the 1.6 volts you'd expect under standard conditions, you get more like 2 volts. Okay, so there's a lead acid battery. Let's just think this is under discharge. Well, if you want to charge up the battery, all you do is remove the load and you push the electrons the way around they don't want to go. So during charging, that is the equation you get. Okay, and you may think, well, where do these lead ions come from during charge? Because I just said they all precipitate out to form lead 2 sulphate. Well, they do, but in reality, remember that this reaction is actually an equilibrium reaction. It goes backwards and forwards. It's just like the equilibrium actually flies very far to the right. So as soon as you form lead ions, they precipitate out as lead sulphate. But if you start using up the lead ions when you are charging the battery, well, that's going to cause the equilibrium to push that way, and the lead the lead sulphate will slowly start to dissolve. So that's what happens during charging of a battery. In actual fact, lead batteries, if you discharge them too much, lead acid batteries, they don't work so well. And the reason for that is if you give them a very deep discharge, you get lots of lead sulphate, solid, and that forms, if you've got lots of it, it forms a coarse precipitate, and that doesn't dissolve so easily. And you're relying on that precipitate to dissolve during the charging up process, as we've seen. So if you run the battery down too much, it's hard to charge it up again afterwards, and it damages it. As you probably know, that lead acid batteries are used in cars, and they're constantly being recharged by the car engine, and they're constantly being used up, by the lights, the starter motor, and all that kind of stuff of the car. But it's not it's not that kind of cell is not something where you charge it up like a mobile phone battery to 100%, and then you run it down to it's like 5% or something. You actually keep it fairly topped up all the time. Another word about that, you can see that this is obviously, you've got liquid sulphuric acid sloshing around here, so it's not very practical in in a lot of situations. It's all right in a car where it can be put on a flat platform, so it's not moving about, not tipping and tilting too much. Obviously it's not going to be useful for things like a laptop or something. Also, it's extremely heavy because you've got lead in it. Again, that's not really an issue in a car engine.